The second step is our definition. So if Pc is differentiable, we know what this means. Okay, because Pc is a single variable function, therefore its differentiability we know very well. Okay, so if Pc is differentiable, we say that f has partial derivative at this point A, which is back to the ith coordinate. So, and the derivative of Pc at 0 is called the partial derivative of the function f at this point A, okay, which is back to the ith coordinate xi. F has independent variables, the first one, the second one, the ith one, the nth one. So this is the partial derivative which is back to the ith coordinate independent variables. Okay, that is to say, we denote this by dif a. Here, this symbol, you can read d or partial, anything you like. I prefer to read it d. Okay, so the I here means xi. Which independent variable you are talking about? Okay, and here the point A means that where you take the partial derivative at this point A. Okay, this is the notation. So by definition, this partial derivative of f at this point A, which is back to xi, is simply the derivative of the single variable function psi obtained previously at 0. Okay, and also this will sometimes be denoted by partial f, partial xi, but you need to indicate which point this partial derivative is taken. So we write a here. Okay, so this is this notation, this notation, and the last notation means the same thing. The partial derivative of f at this point, which leads back to certain independent variables. Okay, and we also denote by fxia or even fia. These two notations are also used frequently. Okay, I remind you to distinguish fia and fia. Here fia is the ith component of a vector. This notation we used before. Okay, but well, the fia here this is our partial derivative. Okay, so this is partial derivative. Okay, of course, some people, as we in our convention, in our notation, a vector valued function is denoted in this way. But some other people prefer to write this as F1, Fn. Okay. So in this case, you should make sure that you are not confused about the notation. Okay. Both notation has this advantage and disadvantage. Therefore, you need to distinguish, clarify the notation from the context. Okay. Now we consider the geometric meaning of these partial derivatives. Okay. Geometric meaning. Okay. So we consider the intersection of the graph of f, which is x, fx. X belongs to the domain of definition of our function f, but because we are considering the existence of partial derivative of f at the point A, so we only require that f is defined in a neighborhood of A. For example, epsilon neighborhood. So x belongs to this epsilon neighborhood. Okay, maybe f is defined in a larger set U. We don't care. We only study the behavior of f near A locally. Okay, so this is the graph of f. So the intersection of this graph is a subset. Actually, this is a surface in this is a surface in Rn plus 1. It is a subset of Rn plus 1, and it is a very nice subset, for example, smooth, or depending on the property of f. Okay, so why this is Rn plus 1? Because f is an n-variable function. Therefore, x, the independent variable x, has n coordinates. So this is n coordinate, and f is a real number. So this together, all this together is n plus 1 coordinate. Therefore, this is a subset of Rn plus 1. This is usually is a surface. So the intersection of this surface, which a plane, we denote by capital pi, which is the first coordinate is valid, and the remaining coordinate is fixed, and the last coordinate y is also valid. Here, x1 and y are real numbers. Okay, so this is a plane in Rn plus 1, two-dimensional plane, because it has two variables, x1 and y. Okay, so the intersection of this graph and this plane is a curve. We can draw a picture here. To draw a picture, so how to make a higher dimensional picture? This is y. This is, we hope this is x1. Maybe this is x2, but only two-dimensional. Okay, we want to higher dimensional, so we can use this single axis to represent x2, xn, n minus 1 dimensional. Okay, dimension. Therefore, this is the point. This is the point A2, An in the x2, xn space. Okay, so this capital pi is x1 values and y values. Therefore, this is a plane. Maybe I change the color. This is a plane here, And our graph of f, is a maybe is a surface I draw by using red. So this is capital GF, the graph of f. Okay, so this part is the intersection, which is a curve. Okay, a curve in Rn plus 1. So the tangent of the point corresponding here, this point is A. Okay, and here is A1. Okay, so the tangent of the intersection, this curve at this point, is a vector. This is the tangent direction. So what's this curve? This curve we denoted by gamma. So gamma, the equation of this gamma is gamma of t equal a plus te1, and Pct is our function defined used in the definition of partial derivative. What is Pct? Pct we record here. Pct is fa plus te1. Okay, but we defined dif in the definition. Therefore, here is tei, but for simplicity, we consider the case I equal to 1. So the Pct is te1. Okay, I need to remove erase this to make space for our discussion. Okay, so in component, if we write this curve component wise, this is exactly a1 plus t, a2 unchanged, an. The last coordinate is our Pct. Pct is the one we recorded there, equal to a f at the value of a plus te1. So the tangent here, gamma t, gamma, the derivative is 1, 0, 0, and the last one is the derivative of no, this is 0. Sorry, I lost this, and no, sorry, which is the first derivative with respect to t, derivative with respect to t is 1. The other a2 an independent of t, therefore the derivative is 0. So 0. Sorry, 0, 0. The last one is the derivative. Here is 0. Sorry. The last one is the derivative of Pc at 0, which by our definition is exactly the first derivative of f at this point A, partial derivative. Okay, so therefore the slope of this tangent with respect to the x1 axis, slope of this tangent with respect to the x1 axis slope of the tangent with respect to x1 axis is d1 f a. So this gives the geometric meaning of partial derivative. That is to say, the partial derivative of a function f defined near a is the slope of the curve. Okay, the curve is the intersection of which of the graph of the function and the plane, the corresponding plane. Okay, so this gives the geometric meaning or geometric interpretation of the partial derivative. Here we use the partial derivative with respect to x1 as example. With respect to the other variables is the same. Okay. And of course, here we discuss n plus 1 dimension. If you feel difficult, you can restrict yourself to the case n equal to 2. Now, that will be much easier to draw the picture. You don't need to use a single axis to represent higher dimensional space. But if you want to graphically study higher dimensional problem, you have to do this. Okay.